Hello science fans! Today we explore single-phase motors. What are they, you ask? Well, they are electric motors. They run on a single source of alternating current. This is the power in your walls. It is super common. Amazing, right? You see these motors everywhere. Seriously, look around your home. Your trusty blender uses one. So does your washing machine. Even your garage door opener. They are the unsung heroes. They make our daily lives easier. They perform so many tasks, quietly and efficiently most times. Why are they so important? Well, consider your refrigerator. It keeps your food cold, right? A single-phase motor powers its compressor. Without it, no cold food. Think of a world without them. Many conveniences would vanish. They are vital for modern living. Science is all around us. Now, these motors are clever, but how do they really work? What goes on inside? It can seem like magic, but it is all science. To understand them better, engineers use a special tool, a kind of electrical blueprint. Let's find out more. So how do we peek inside? How do we understand these motors? We cannot just open them easily, not while they are running anyway. There are wires and magnets, and electricity flowing through. It is a bit complex. We need a simpler way, a way to model it. This is where equivalent circuits come in. Think of an equivalent circuit. It is like a map for electricity, a road map for electrical current. It shows the path electricity takes. It shows the important parts, the parts that affect the motor. It simplifies the complex reality. It is a very useful tool. Imagine you are building with blocks. An equivalent circuit is similar. Each block represents a part of the motor's electrical nature, like resistance or magnetism. We put these blocks together. This forms a model. This model behaves like the motor. Electrically speaking, that is. This motor map is super helpful. Engineers use it all the time. It helps them predict performance. How much power will it use? How fast will it spin? Will it get too hot? The circuit helps answer these, without building many prototypes, saving time and resources. Science. Let's look at our motor map. The equivalent circuit has key parts. First, there is the main winding. This is a coil of wire. It is the primary workhorse. When electricity flows here, it creates a magnetic field. This winding has resistance, like friction for electricity, and it has reactance. Then there is the auxiliary winding. This is another coil of wire. It is also called the start winding. Single-phase motors need help starting. They cannot start on their own. The auxiliary winding provides this. It creates a second magnetic field. This helps get the motor spinning. It also has resistance and reactance. Very important for starting. The circuit also represents the rotor. The rotor is the spinning part. This is where motion happens. Its electrical properties are shown. These properties change with speed. This is represented by resistances and reactances that depend on slip. Slip is the difference in speed between the rotor and magnetic field. It is all connected. Other important bits are there too. There is a part for core losses. Motors are not perfectly efficient. Some energy is lost as heat, lost in the motor's iron core. This is shown as a resistance. There is also magnetizing reactance. This represents the magnetism needed to make the motor work. All these parts tell a story. So we have these parts. The main winding, auxiliary winding, rotor parts, core loss parts. How do they all work together? The equivalent circuit shows this. It shows how they are connected. It models the flow of electricity from your wall outlet through the motor's components and how it creates torque to spin. Engineers find this circuit invaluable. It is a powerful analytical tool. They can use math with it, formulas from electrical science. They calculate motor current, they predict starting torque, they can estimate efficiency and the motor's power factor. All from this one diagram. Consider that. Let's imagine a simple case. What if the voltage changes? Maybe it drops a little. How does this affect the motor? The equivalent circuit helps us see. We can calculate the new current, we can see if torque changes, or if the motor might overheat. It helps us understand consequences. It is predictive power. So, let's recap this journey. Single-phase motors are everywhere. They are in many appliances. An equivalent circuit is a model. It is like an electrical map. It helps us understand them. Each part, like resistance, reactance, represents a real motor property. It helps us design and analyze. Isn't science cool? Yes.